Today we will look at the convergence of steepest descent method. Right? Here we in theorem 5.2.3 we use the steepest descent with exact line search. Okay, and we use steepest descent with exact line search to minimize a quadratic function. Now you will see what is the convergence. Now you can see that the convergence rate depends on the Hessian matrix of the problem. Okay, so we look at the details. Here we apply the steepest descent with exact line search. To minimizing the quadratic function fx equal to 1 over 2 x transpose qx plus p transpose x, where q is positive definite. When we assume that q is positive definite, we can guarantee that there is this is a minimization problem, not maximization problem. So the minimum exists. When we write a matrix is greater than 0, it means this is it means the matrix is positive definite. Okay. Then the result is that for any starting point x naught, the method converges to the unique minimizer x star of the problem, and now we express the convergence rate instead of using the difference in the minimizer, we express the convergence rate of the steepest descent method in terms of the reduction of the objective function. Okay, this is a little bit different from the convergence analysis, the normal convergence analysis here, because we instead of looking at the convergence of the iterate xk, here we look at the convergence of fk, the objective function fk. Right? Okay, and we find that the fxk, fxk plus 1 minus fx star. So this is positive, right? Because fx star is the minimum. Therefore, any fx is greater than fx star. So when we write this, the fxk plus 1 minus fx star is always positive. So we don't need to put the absolute value sign. Okay, fxk plus 1 minus fx star is less than or equal to the rate constant, which is the square of the capital A minus A divided by the capital A plus the small a, multiplied with fxk minus fx star. Now you can see this is the according to the definition of a linear convergence, this is a linear convergence, right? This is a linear convergence, and r is equal to 1. Okay, so r is equal to 1 from this expression. R is equal to 1, and the rate constancy is equal to the square of a minus a divided by a plus a squared, right? Okay, this is the rate constant. Now we will see, we will look, where the capital A is the largest eigenvalue of the Q matrix, and the small a is the smallest eigenvalues of the Q matrix. Now you see, when for linear convergence, we have to consider the rate constant, okay? Because the convergence of linear convergence also depends on the value of the rate constant. Whereas if you can see, okay, whereas in the case of superlinear convergence and quadratic convergence, we don't okay, we don't concern much about the rate constants, right? Because once for superlinear or the quadratic convergence cases, you can say that when the error is getting small, right? If the difference between xk and xk star is small, then it converges very fast, as you can see when you can see that when you implement the Newton-Raphson method, right? When the okay, but here, but linear convergence is very different because linear convergence, the convergence reduces slowly, steadily, but then whether it's fast or slow depends on the rate constant c. The rate constant c, we know that it has to be less than 1. It has to be between 0 and 1. But then if the rate constant c is approaching 0, then linear convergence can be very fast. After this theorem, I will give you an example in which you will see that, okay, how fast it can be, and when it's slow, what's happened, right? Okay, you can see the proof in the reference, okay, but the theorem is taken from National Software. Now you will see that the convergence of the steepest descent. You see that we implement the steepest descent with exact line search. Okay, so that means in every iteration, we make sure that the cost function is reduced to the minimum in that direction, in the selected direction. Okay, and then but then we apply this to a simple quadratic function. The convergence rate still depends on the H1 matrix of the problem, which can be fast or slow. Right? And okay, now we will see what happens. Then because the H1 the Q matrix is positive definite, and therefore all the eigenvalues are real, right? And when Q is positive definite, then all the eigenvalues are real numbers, are positive real numbers, right? So when the largest eigenvalue and the smallest eigenvalue are very close, then you see that the rate constant, what happens? The rate constant approaches 0. Because when the two A's are very close, then the capital A minus A is very small, right? Yeah. And then when we square that, it's even getting less, getting smaller. Then, but when the capital A and the small a are large, if the difference between the capital A, the smallest eigenvalue, and the largest eigenvalue are large, then you can see that the rate constant C is close to 1. So in that case, the steepest descent can be very slow because, right? Now we will see what happens. Now consider the function of two variables. If fx fx is equal x1 squared plus cx2 squared, then okay, when c is equal to 1, fx becomes x1 squared plus x2 squared. What is the H matrix of this one? What is the H matrix of this one? What is CUEE matrix? What is CUEE matrix? One over two x transpose QX plus P transpose X. So what is the CUEE matrix? So CUEE matrix is a diagonal matrix, right? Q is a diagonal matrix, so this is 2 and 2, 0, 0. So what is the eigenvalues of the CUEE matrix? The eigenvalues are 2 and 2. 2 and 2. So the capital A and the small a are, so the largest eigenvalue is equal to the smallest eigenvalue. Now you can see that the rate constant C in this case is 0. Right? The rate constant C is 0. So what happens then? Now you can see that in this case, if we use the same technique as we did in the last period of in the last lecture. So now you can see when we minimize this, if this is the okay. So what is the shape of level set on the plane x1, x2? What is the shape of the constant contour fx equal constant on the plane x1, x2? What is that? It is what? What is the shape of the constant contour fx equal to 0 on the plane x1, x2? Fx f is the set of x1, x2 such that fx fx1, x2 is equal to constant c. What is the shape of this? What is the shape of this? It's a circle, right? Then it's a circle. When it is a circle, then when we minimize this, suppose we start from any initial condition, any x naught. Suppose we start with the initial point x naught on any point on the circle. So what is the x1? How can you find the gradient of this? We draw the tangent line, and so the gradient is perpendicular to the tangent line, right? And from geometry, a line that is perpendicular to the tangent line passes through the origin of the circle, right? Am I right? So the gradient, you can see that the search direction in this case just go through the right? This way. So what is the minimum of this when you okay in this direction? What is the minimum? Is exactly at the origin, the origin which is the minimizer of this problem. Right? So that means what? So okay, so in this case, you can see that the steepest descent converges within one iteration. The steepest descent converges within one iteration. Okay, so Okay, from geometry, we see that x1 is equal to the origin, which is the minimizer of this problem. In one iteration. And now you can see that here in this case, the constancy is 0, right? Which is very rare, but this can happen, okay? Now we look at another example in which when C is not 0, now when C, let's say is equal 100, when C is equal 100, well, you can take 100. So what is the Q matrix? Am I right? Am I right? When fx is equal to x1 squared plus x2 x2, so if we write it in the quadratic form in this case, then it's 1 over 2 x transpose. This is the 2, 0, 0, and 2c, right? Am I right? Is x. Is this correct? Is this correct? Yes. So when in this case, the Q matrix is the H matrix is still diagonal, right? But then with the Q11 is 2 and Q22 is 200. So what are the eigenvalues of this matrix? Now you see that A is equal to 200, right? And small a is 2. So what is the rate constant? The rate constant C is okay. So the rate constant, the capital C, the rate constant C is what? Is right? Close to 1. You see that when the larger the constant C is, the larger the constant C, then the nearer the value of the value of the rate constant C is very close to 1, right? So now what's happened? Then if we draw the constant contour of this function, the level set of this is 0. Okay. Now you will see it forms the level set takes an ellipse, right? The constant only becomes an ellipse. What is the shape? It look like does it look like this? Does it look like this? Does it look like this? This is the constant contour. This is where, and this one, this is where the x1, x2, right? Such that the x1 square plus 200 x2 square is equal to constant c, right? The ellipse take this shape, right? So now you see that here, if we minimize this, if we draw this, you draw many ellipses. Now you will see that it takes the steepest descent with exact line search, producing a zigzagging trajectory towards the iteration, and therefore it takes it takes a long time. Right? If we go to the method that we do as in the last, if we do like this, then you see that when it's if the constant contour is very narrow, is very steep, is very narrow, then it's right. Example, if, for example, if you can choose any point, this is 0, then what is this? When you this 0, then it's the gradient take this one. This is the S naught, right? Then what is x1? You go along this direction, and then perhaps you have reached some point here. This is x1, right? Okay, this is x1. This is x1. And from x1, then, okay, then you say this is x1 and this is x naught. This is it. Then from this, you'll see if you take this and then it go, this is the S1, right? X1, S1, then now you see that it reaches this point. If you do this again, then it becomes, the trajectory becomes like this, will be like this. The solution is like zigzagging. Then it takes many iterations. You can do that you can confirm this by computation. Just write a program in MATLAB about 10 lines, and you'll see this. And if you plot the trajectory on the plane, you will see this. What happens? Okay, you can see this you can see this more clearly. Okay, when you do that in MATLAB, only 10 lines of MATLAB code, and you plot it on the MATLAB. Okay. You can see that. Now, okay, this is the convergence. Now you will see this is when we apply this. Now you can see that when we apply the steepest descent with exact line search, this is the best we can implement it, right? This is the best way that we can implement it in terms of the function reduction. Because in this, okay, so in homework you will see that to solve an exact line search, okay, to do exact line search, or to implement exact line search, it takes many iterations in one dimensional search, right? When you reach the to the minimum in each direction, in each search direction, you spend you have to compute the function f many times, because okay, that's what we do, and this is what happens. And this is so we implement the steepest descent with exact line search. and we apply that to a very simple nonlinear, nonlinear function. We apply that to quadratic function. Then the convergence depends on the convergence. Okay, sorry, depends on the Hessian matrix of the objective function, right? Then it can be fast, it can be slow. Linear convergence. Although the rate of convergence is linear, but it can be fast or slow depending on the constant c, right? Depending on the rate constant c, right? Which is expressed in terms of the largest eigenvalue and the smallest eigenvalue. Next we will, let me finish this. So for the general nonlinear function, we can also, it's possible to show as well that the steepest descent method with exact line search converges linearly to the rate constant c, which is bound by this number. Which is bounded by this number. Oh, sorry. Where the capital A and the small a are the largest and smallest eigenvalue of the Hessian matrix at the minimum point, at the point x. Okay, we can prove that, but we. Okay, so that's this is the end of the lecture of this part. We will have 2 minutes break, and then we start the recording the new session again on Newton method.